All right, let's get right into it. Welcome to this explainer. Today we're unpacking a massive, fundamental shift that is absolutely required to secure modern microservices. Look, if you've ever spent hours, maybe even late into the night, trying to figure out why one service is stubbornly refusing to talk to another, only to discover it was an impersonation or identity issue, well, you already know why service identity matters so much. We're living in a time where the explosion of microservice architectures means applications have been completely fractured into dozens, hundreds, or even thousands of smaller components. And because of this massive scale, machine-to-machine communication now absolutely dwarfs human-to-machine traffic. It's not even close. So in this world, knowing exactly who is calling is not just some nice-to-have feature. It is literally the bedrock of your entire security architecture. We're going to explore how to actually implement service identity, moving completely away from the outdated, frankly dangerous idea of a secure network perimeter and fully embracing a zero-trust mindset.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the zero-trust problem, then define service identity, look at application-level authorization, explore the client credentials flow, move on to infrastructure-level authorization, and finally, how to choose your strategy.
Kicking things off with Section 1. The zero-trust problem.
We really need to start by establishing a harsh reality about modern system architecture. The days of trusting everything inside a network perimeter, they are completely gone. The perimeter itself is just an illusion at this point, and this brilliantly illustrates why. Let me tell you a story about a hacker named Alexei that perfectly shows why perimeter trust is so incredibly dangerous. So Alexei found a breach point in a company's infrastructure. It was an exposed debug pod just sitting inside a Kubernetes cluster. Now, you might be wondering, why on earth was it exposed? Well, it was left over from a late-night troubleshooting session, entirely forgotten by the developers, and it was sitting there without a password simply because it was deemed, quote-unquote, safely inside the firewall. This is the false security of monolithic perimeters at work, right here. From that compromised pod, Alexei scanned the internal network and targeted the billing service. He noticed something interesting. The billing service accepted requests from the order service to process invoices, but it didn't check for a digital signature. It didn't check for a cryptographic certificate. No, it just looked at a plain text HTTP header that read X service name, order service. Seriously. So Alexei just created his own fake service, injected that exact same plain text header into his malicious requests, and sent them right off. The billing service blindly trusted the incoming request without any cryptographic proof, couldn't tell the difference, processed the fake invoices, and leaked real financial data.
The days when we could trust everything inside the perimeter are gone. I want to linger on this for a second, because the reason Alexei was so successful is due to a concept known as optimism. Historically, software developers and network engineers designed systems with a tremendous amount of optimism. The working theory was basically that if a request somehow made it past the outer firewall and was traveling on the internal network, it was inherently friendly. But in modern, highly distributed systems, this optimism is a fatal flaw. Hackers absolutely love optimism. They thrive on the assumption that internal traffic is safe traffic. If your services cannot definitively prove who they are, you are basically accepting anonymous API calls and just crossing your fingers, hoping they are from a friend.
Moving on to Section 2. Defining service identity.
To stop exploits like Alexei's from happening, we rely on service identity. Service identity is defined as a unique, verifiable identity assigned to a service instance or an application component. Think of it exactly like a human passport, but for your applications. Just as user identity determines who a human is, service identity does that exact same thing for machines. It brings order to the chaos by giving each service a way to definitively prove who it is. But how is this identity actually tied to the component? Well, typically, it's generated right at deployment time. It gets mathematically tied to the workload service account, and conceptually, it's stored in secure memory or delivered as a secure volume mount directly into the container. It allows a service to say, yes, it's really me, and here is the cryptographic proof. Because honestly, without this verifiable proof, your authorization, your auditing, and your secure communications are all just guesswork.
So, to build this passport system properly, we rely on 4 fundamental pillars of service security. First up is identity itself. A concrete example of this would be an X.509 cryptographic certificate, or a securely signed token that actually holds the service's name. Second is authentication. This is the act of verifying that identity. If the identity is the passport, authentication is the border agent verifying you actually look like the hologram on the photo. In systems, this is typically done via a mutual TLS handshake, which proves that the caller actually holds the secret private key associated with that certificate. Third, we have trust anchors. I mean, someone has to vouch for the identity, right? This is usually an internal certificate authority, or CA. If the calling service and the receiving service don't share the same trust anchor, they fundamentally cannot trust each other's certificates. And finally, we have the scope of identity. This determines how widely an identity is shared. A wide scope means a whole massive deployment shares a single generic identity. It's super easy to manage, but the blast radius is huge. If one pod is compromised, the attacker has the keys to the kingdom. A narrow scope, on the other hand, assigns a unique identity to every single individual pod. It is incredibly secure, but managing thousands of unique, rapidly changing identities is, as you can imagine, incredibly complex.
All right, Section 3, Application-Level Authorization.
Now we're going to look at the first of two philosophical approaches to actually fixing this vulnerability and implementing identity, and that is writing security checks directly into the application code. Now, why would an organization choose this? Generally, it gives the application developers ultimate, fine-grained control over their specific security logic without relying on external infrastructure. When developers handle this, they generally use one of three patterns. They might use API keys, which are static strings. They might use custom request signing, which involves cryptographic signatures. Or they might use the OAuth 2 client credentials flow, which is token-based. Let's break down exactly how these work.
First, let's talk about the API key trap. Look, API keys are incredibly simple to implement. It's just a unique string included in a request header. But using an API key for internal microservices is literally like leaving the key to a bank vault under a neon welcome mat. It's just asking for trouble. They act like a simple password, but they are completely static. If Alexi intercepts a static API key, or if it gets leaked in a log file, the system is just as compromised. Anyone can use it. Plus, rotating them at scale is an absolute nightmare. To change an API key, you have to update the configuration on both the calling service and the receiving service simultaneously without causing downtime or dropping any requests. And on top of all that, the string itself carries absolutely no useful metadata about who the caller actually is.
So, a much stronger application-level method is custom request signing, which relies on asymmetric cryptography. Now, I know that sounds intimidating, but the logic is actually pretty elegant. You have a private key that stays an absolute secret and a public key that you share with everyone. In step 1, the calling service takes important parts of the request, things like the URL path and the current timestamp, and scrambles them into a digital signature using its secret private key. In step 2, that signature is added to the HTTP header. And then in step 3, the receiving service doesn't just blindly trust the caller. Instead, it uses the caller's public key to unscramble that signature. If the unscrambled data perfectly matches the incoming request, it mathematically proves two crucial things. First, that only the holder of the true private key could have signed it, and second, that the request was not altered by anyone in transit.
But even mathematically secure signatures have a catch. What happens if an attacker intercepts a perfectly valid, correctly signed request to pay an invoice and just sends it again 5 minutes later to generate duplicate payments? That is called a replay attack. The signature is mathematically valid, so the math alone won't save you. This is exactly why we included a timestamp in the signature on the previous slide. To stop a replay attack, your application logic must look at that timestamp and strictly reject requests that are too old. But consider the infrastructure required to make timestamp checking work across a massive distributed system. You need near-perfect clock synchronization across all your servers using the Network Time Protocol, or NTP. If your server clocks drift apart even a little, a valid request might look old and be falsely rejected, or an old request might sneak through. It is definitely safer than an API key, but it takes an incredible amount of careful, flawless coding by your developers.
Which brings us to Section 4, the client credentials flow.
Now, what's really interesting here is how we can delegate trust to a third party to avoid building all that custom cryptography from scratch. This is the industry-standard way applications handle identity via tokens, the OAuth 2 client credentials grant type. Follow the conversation happening here. Let's say the billing service needs to talk to the payment service. Instead of managing complex key exchanges directly, the billing service goes to an identity provider, or IDP. Think something like Keycloak or Auth0, and says, "Hey, here are my credentials, issue me a token." The IDP validates those credentials and hands back a temporary JSON Web Token, or JWT. This token is fascinating. It has a header defining the algorithm, a payload containing specific claims like who the subject is and exactly when the token expires, and a cryptographic signature. The billing service then attaches that JWT to its request to the payment service. Finally, the payment service validates the token, typically by fetching the IDP's public key to verify the signature. It's incredibly fast, it follows a strict industry standard, and because the tokens have a very limited lifespan, often just a few minutes, the security window for an attacker to steal and use a token is incredibly tight.
Next up, Section 5, Infrastructure-Level Authorization.
So, we've talked about writing security logic into the app, but there is a second, more modern approach to plugging the zero-trust gap. This approach takes the burden of responsibility completely away from your application developers and delegates it to the platform. Here we are looking at API gateways, like Kong or Apigee, and service meshes, like Istio or Linkerd. It's absolutely crucial to understand the distinction here. API gateways typically sit at the edge of your network, managing external traffic coming in. Service meshes, on the other hand, manage the lateral, service-to-service traffic deep inside your network. Think of these components like highly trained, heavily armed security guards stationed at the doors of every single room in a building. They intercept every single request, rigorously check who is calling, and verify what they are allowed to do, all before the request even gets close to your application's business logic.
Let's dive into the details of exactly how a service mesh achieves this without modifying the app at all. The mesh deploys a small proxy container, which is known as a sidecar, right next to every single service instance in your cluster. By using low-level networking rules like IP tables, this sidecar transparently intercepts all incoming and outgoing network traffic. When your app tries to talk to another app, the sending sidecar intercepts the request and performs a mutual TLS handshake with the receiving sidecar. They exchange those X.509 certificates, verify each other against the centralized trust anchor, and then establish a secure encrypted tunnel. The mesh's control plane automatically rotates these certificates behind the scenes, completely eliminating that nightmare of manual API key rotation we discussed earlier. The true beauty of this architecture is that your application code remains completely untouched. The app doesn't know anything about MTLS, certificates, or token validation. It just talks over local, unencrypted HTTP to its sidecar, and the infrastructure automatically handles the entire heavy lifting of zero-trust security.
And finally, Section 6, Choosing Your Strategy. So the crucial point is understanding the real-world trade-offs between these two approaches, specifically when it comes to organizational impact and system performance. Application-level authorization gives you highly flexible, fine-grained control, but it requires training every single developer in your organization to write flawless cryptographic code. It is highly prone to human error. If just one team forgets to implement a signature check, boom, you end up with an Alexi situation. Furthermore, processing cryptography in the application thread consumes CPU resources directly from your app. Infrastructure-level authorization, on the other hand, completely shifts the organizational burden. You get foolproof, consistent enforcement, automatic MTLS, and zero app code changes. However, running a service mesh requires a highly skilled, dedicated platform team to manage complex tools like Istio. And performance-wise, while you offload the cryptographic CPU processing away from the app, routing traffic through two sidecar proxies does add a slight network latency overhead to every single request. Ultimately, you have to decide which trade-off fits your engineering culture.
To briefly synthesize our journey today, we've seen exactly why the old network perimeter is a dangerous illusion in the era of microservices. We explored how defining a cryptographic service identity acts as a literal passport for your applications. And we weighed the complex trade-offs between asking your developers to write custom authentication code versus letting a powerful service mesh handle it transparently. Remember Alexi the hacker? Please, don't let an exposed debug pod be the end of your company's reputation. I want you to look closely at your own architecture right now. If an attacker breached your perimeter today and gained access to your internal network, would your services actually know who is really calling them? Or are they just blindly trusting a header? Security emerges from thousands of small decisions, and implementing strong service identity is absolutely the most important decision you can make. Thanks for joining me on this explainer.